In instance selection, how does active learning determine which unlabeled instance to query the labels? There have been many proposed ways of formulating such query strategies. The simplest and most commonly used query framework is uncertainty sampling. In this framework, an active learner, so the model, queries the instances which it is least certain how to label. For example, in a binary classification problem, uncertainty sampling simply queries the instances whose predicted probability of being positive or negative is nearest to 0.5. For problems with 3 or more class labels, a more general uncertainty sampling strategy might be querying the instances whose predictions are the least confident. Formally, let's say y hat is the class with the highest predicted probability. Then the model will select the instances where such highest probability is the smallest. Now let's look at an example. Here are 4 instances in a 3-class classification problem. You can see the predicted probability for the instance to be each of those classes. Which one would then be selected using the least confidence method? Well, we will first check which class each instance has the highest probability, right? So there are the classes. These are the classes with highest predicted probability. And then we look for the instance where the highest probability is smallest, which is x2. So we will select x2 first. The instance with the second least confidence is x3. So if we can select 2 instances for the labeling, then we will go for x3 next. The criterion for the least confidence strategy only considers information about the most probable label. Thus, it effectively throws away information about the remaining label distribution. Another sampling strategy, margin sampling, considers the 2 most probable labels. Intuitively, instances with a large margin in the prediction for the 2 most probable labels are easy, since the classifier has little doubt in differentiating between the 2 most likely class labels. Instances with small margins are more ambiguous, and knowing the true label would help the model discriminate more effectively between them. For this same example, which instance has the biggest margin in the prediction for the 2 most probable labels? We first calculate the margin like this. So we would first select x2 again. For problems with very large label sets, the margin approach still ignores much of the output distribution for the remaining classes. The sampling method that takes into account probability prediction for all classes is entropy-based sampling. Entropy is an informative theoretic measure that represents the amount of bits needed to encode a distribution. As such, it is often thought of as a measure of uncertainty or impurity in machine learning. Probability distributions that are more even, meaning more uncertain, would have higher entropy. For binary classification, entropy-based sampling reduces to the margin and least confidence strategy. However, the entropy-based approach generalizes easily to multi-label classifiers. In the same example, here is the result we will get using entropy-based sampling, and we will select x3 for labeling. Apart from uncertainty sampling, there are some other sampling methods. One of them is called query by committee. The goal is to find the instances that minimize the model hypothesis space. What it does is first train a committee of models using different initial data, and then the models will vote for different instances to be queried. The method then selects instances that the different models disagree the most. The intuition is simple. Once we get the label of this instance, we best resolve the disagreement, making the models more agreeable to each other. Another method is called expected model change. The goal is to find instances that impart greatest change to the model if the label is new. Model change can be measured by the length of the training gradients. The strategy can therefore be applied to any learning problem where gradient-based training is used. The intuition behind this framework is that it prefers instances that are likely to most influence the model. For example, have the greatest impact on its parameters. Of course, since we don't know the true label, we need to calculate the expectation over the possible labels. Apart from all those methods, there are some others like expected error reduction, variance reduction for querying instances to label. If you're interested, you can take a look at the survey paper from Setos. So far, we have been talking about active learning settings where the human labeler makes no errors. That is, they always provide the true labels. In the crowdsourcing setting, we know that this is not the case. So in the setting of active learning from crowds, we need to consider the selection of not only the most informative data instances for model training, but also the most reliable workers to label the instances. In the selection of instances and workers, which one do you think is more important? On the slides, you can see experimental results comparing different configurations on 3 datasets. For each dataset, the horizontal dimension shows the number of iterations in the active learning cycle, and then the vertical dimension is the performance of the model. 4 experimental configurations are compared with or without the selection of instances or workers. The best performing configuration is the one that actively selects both instances and the most reliable workers, of course. Comparing configurations where only instances or workers are selected, we can see that selecting the right workers is more important than selecting instances. Now, having talked about ways to get high quality data for machine learning, let me take a step back and ask you a question. Do we really need high quality training data? The answer might seem obvious. Sure, right? The higher quality of our data, then the better we can train our models. But what if getting the data comes at a huge cost? Like many examples in reality. We need a good trade-off between data quality and labeling cost. And if we consider this trade-off, in fact, getting high quality training data is not that important. Data quality is important when it comes to model testing or evaluation, when we need to have a good measurement of how well the model works. But for model training, what we care most of the time is optimizing model performance, not the accuracy of the data. Of course, data accuracy helps, but that can be compensated sometimes by data size. A large amount of low-quality labels might be more useful than small number of high-quality labels. There are a bunch of these methods that would allow us to efficiently generate a large number of low-quality labels. And these include Bootstrap with other classifiers, meaning that we can use some classifier that are not perfectly trained to label instances and use those labels to train our target model. Distance supervision, which means using external databases to heuristically label instances. This is an important technique used in knowledge-based construction. Here we do not go in depth. The other method that I want to talk a little bit about is labeling with patterns or rules generated by humans. It means that we can use patterns to label all the instances with the pattern being present. For example, if we want to label if a chemical causes a disease in a sentence, we can think of the following pattern. If there is a word not that occurs between the detected chemical and disease words, then we can assume that the chemical does not cause the disease. We can write a simple labeling function to apply this pattern labeling to all instances that we have. Compared to labeling individual instances, this is more efficient. And in fact, in some experiments, researchers have found that this approach is 2.8 times faster than labeling individual instances. And the larger number of labels also result in better model performance. Stanford has recently developed a system that allows to aggregate many labeling functions by learning the accuracy of individual functions and the correlation between them. And this is similar to learning worker reliability. But here, the target is to find the reliability of labeling functions.